All right, welcome. We're going to talk today about some work on advanced visualization and data analysis of HPC cluster and user application behavior. This is work carried out in the National Science Foundation funded Cloud and Autonomic Computing Industry University Cooperative Research Center, which is a multi-university, multi-industry organization. The work was done at Texas Tech University with funding from Dell Technologies in partnership with Intel. And the work that you hear about today has been done by graduate students Jie Li and Nan Yen with guidance from their faculty advisors, Dr. Tommy Deng and Dr. Yong Chen, and myself, and industry collaborator, John Haas. So we're going to talk today about an overview of the project, where it's been done and in what context, the facility that we used. We started this work with extensive simulation, but have tested it in our facility, as we'll describe. We'll go into a lot of detail on data collection and management with a large amount of data and visualization in the context that we think will is prime for rapid adoption. And the context, as I said, is the High Performance Computing Center here at Texas Tech University. Here we run several hundred nodes, about 240 nodes of AMD-based cluster providing almost a petaflop, and an older cluster with about half that computing power. We also have extensive GPU capabilities, which we're just bringing into this framework. So we'll talk primarily about the CPU monitoring. The project idea is to develop a cutting-edge visualization, monitoring, and management solutions for high-performance computing center systems to understand the status of the platform and how the applications are running on it, and to provide insight into interactions among the platform components. This goes into much greater detail, orders of magnitude more detail than previously available monitoring projects, due to the greatly increased level of detail available from modern baseboard management controllers, primarily through the Redfish standard telemetry feature that allows collection of a large amount of data and correlates that through API and CLI interfaces that we've produced to the behavior of HPC job schedulers and application. So next, we're going to have graduate student Jie Li talk about data management and collection.
The corner nodes are equipped with iDRAC9, which is an advanced baseboard management controller. The monitoring data that obtained from iDRAC9 can be streamed or pushed from each node, which means computer node can actively send metrics to the monitoring node instead of a passive and inefficient pull method. The advanced iDRAC9 provides over 180 data metrics related to server and peripherals operations, including power consumption, CPU usage, I/O operations, etc. Unlike metrics from previous iDRAC model, where we must attach timestamp to metrics at the client side, iDRAC9 metrics are precisely timestamped and internally buffered to allow highly efficient data streaming with minimal network loading. Note that with higher granularity and more available metrics, the total volume data is much higher than previous iDRAC. This is a picture showing the process of data collection and analytics using iDRAC9, which is basically the same process with our project. We will develop ingest collectors, set up database, and realize telemetry metrics. To quantify the challenge of the data management, we summarize the number of metric records collected from our system. It is based on the available sensors and the total number of nodes in the cluster. For the corner partition, there are 12 available metrics for each node. The data pulling frequency is 60 seconds. When multiplied by the total number of nodes of corner partition, which is 460, we will have a total of 1.9 billion records of metrics each year. For Nakona partition, the total number of available metrics is over 180, and the pool frequency is more granular, which is 5 seconds. For the whole partition with 240 nodes, the total number of records collected is about 31 million for 1 hour, over 700 million for 1 day, and 22 billion for 1 month, and over 268 billion for 1 year. The total number of records in Nakona is about 100 times of that in Kona. The higher data volume requires improved methods for data storage, compression, and query. We've explored the following ways to improve the availability of the monitoring data. Specifically, we use NVMe drives for data collection, ingest, and database. It provides a faster data access. We also explored using timescale DB, an optimized relational database for time series data to store the monitoring metrics. The built-in compression is used to reduce the data volume. From our experience, we observed that the average compression rate for these metrics is over 85%, as shown in this figure. The compression significantly alleviates the data storage pressure. Besides using faster storage and the database optimized for time series data, we further developed a master interface to provide easy access to the monitoring data, where the visualization accesses the data through the APIs. Our project architecture currently contains 2 main components, the data collection and the visualization components. We are also working on the automation components. It is a set of automation tools that help system admins with their daily tasks. The data collection component collects monitoring data from each computing node and the resource manager and manages the monitoring data in timescale database. It also provides APIs and accelerates the data queries for visualization and automation. The visualization component consists of a series of visualization applications providing interactive tools for system administrators and HPC users to check the system status. Here I list several techniques used in our project. The data is collected from Slurm and each node through the Redfish API. The collected data are stored in timescale DB. We developed the API service using OpenAPI. Visualization applications are mainly developed in JavaScript, TypeScript, and D3 library. Now I will let the visualization team present the visualization applications in detail.
Visualizing and monitoring data center is challenging due to the size, the complexity, and the dynamic natures of the data. So we are talking about hundreds to thousands of computing nodes and tens to hundreds of computer health metrics that are generated in a matter of every second. Moreover, the system administrators are also interested in capturing the physical layout of the center. So when a problem happens, they would like to know where it is located. Finally, we are dealing with the data coming from different sources. For example, we are talking about the job scheduling data coming from Slurm and the computer health metric coming from IRAC. Overlaying those data will provide the system administrator supplementary views to tell the stories, such as a high CPU temperatures reading associated to CPU bound jobs. High memory usage might be related to users who run chemical simulations. This slide shows you some example of visualization that we built in the past 2 years working with the expert in high-performance computing and their associate. Why there's no single best visualization for everything? Each visualization here will tackle the different aspect and requirement of the system. In this presentation, we will demonstrate a subset of this visualization. My PhD student Ngân Nguyen will show you the selected visualization in the next slides.
The first visualization I would like to introduce is the parallel coordinate. In parallel coordinate, each dimension will be displayed as the vertical axis. For example, a record of the compute health metrics such as CPU temperature, memory usage, or fan speed is illustrated as curve traveling along those dimensions. In this visualization, we monitor 467 compute in Quanta cluster. Because each compute at specific time will be a record, a large number of curves will be drawn on the parallel coordinate. Thus, we cannot observe the distribution of each dimension. Therefore, we draw a violin chart on each axis. So according to the violin chart, we can see that the fan speed 1, 2, 3, 4 actually have the same distribution, which means the fan speed 1 is enough to present for the other fan speed. By looking at the distribution of those axes, the CPU1 temperature is mostly higher than the CPU2 temperature for this system. So this is another visualization. So instead of focusing on the health metric, the job viewer provides a snapshot of the network between the user and the compute. The job viewer includes three main components: compute, user, and link. Compute is represented as a circle colored by the metric values. The color scale is from purple to red, corresponding to the low to high value. Only one metric is selected at a time in this mode. The border thickness of the circle is present for the number of the user utilize the node. As this one, the compute is grouped by the rack. Another component is the user. The user are listed in the center of the network. The list is ordered by the number of the job. Please note that the username in this presentation is coded for the demonstration purpose. Admin or root user is able to see the real username. The last component of the job URL is the link. The link is the connection between the user and the compute when the user had a running job on that compute. Job viewer provide a basic interaction like hover the compute or hover the user to highlight the user versus the compute relationship. User can control the time which they interested to see the snapshot. And this menu can enable to simulate the historical data from the existing record. A user can submit multi-job, and a job can run on multi-compute. So it is handy to see the list of the job when interact with the visualization. The user will be auto-highlighted with a thicker border when the job has just started at the current time point. In this example, compute running the job ID 1935973 have the CPU1 temperature steady during the job running time. The value drops after the job is finished. This is useful when researching the characteristic of the job running by particular user. For the next use case, the inconsistency metric will be highlighted. In this snapshot, the color embedded display the fan speed value. The node for 33, 34, 35, and 36 has the highest fan speed. The special detail here is those four nodes are placed near each other physically. When checking the CPU2 temperature, only the node for 33 had the high CPU2 temperature. And please note that on this system, the CPU2 temperature are usually lower than the CPU1. So this is an abnormal case. At this time, instead of switching between metric to analyze it, if 3 or the node is heating up due to the node 433 or not, the job viewer provide the option to show all the metric at the same time with the radar chart. How metric is shown as the axis in the radar chart. So we have the distinguished radar shape for the data. Apply the clustering algorithm, the outlier will be stay out. The node 33 has the distinguished radar shape. From here, we can jump to the conclusion that the other compute has heating up and raise the fan speed due to the high CPU2 temperature at the node 433. In here, the node 433 is the radar with the red color, and the other node near it have the pink color. Another application of radar chart is to analyze the user characteristic. For example, the user 14 is different from other user at the high memory uses. So in order to enhance the usability of our visualization, instead of the web-based visualization, we choose Graphene, a well-known open source platform to implement our visualization plugin. Graphene supports multiple database communication, and currently we have 4 plugins available. We will introduce 2 plugins in the following slide. The first plugin is the parallel coordinate. Similar to the web version, the Graphene plugin will display all the metric queried from Graphene. For the small number of the node, user can color the parallel coordinate by the node name. The axis can be toggled by provided the left panel. Also, user can can always switch into the different color mode. For example, like the color by the metric. In this mode, each curve will be colored by the selected metric. And we also have the simple viewing filter is enabled by just drag onto the particular axis. This demo is show the real-time visualization ability in the last 6 hours of the Nocona cluster. So we remember that we have 240 compute showing on the screen. When filter the power consumption, only 1 compute is showing. The difference from the corner cluster and Nocona cluster is the corner cluster have the CPU1 temperature is higher than the CPU2, while the Nocona cluster is reversed. And it's easy to detect the outlier from the CPU2 temperature. The node 2543 had the high CPU2 temperature compared to the other compute. This happened, actually it's happened quite frequently. And according to the historical record, the data from 2 months ago. And another use case is the node 2659, which report always report 0 on the span speed. This is the issue due to the out-of-date version of the iDRAC on this node. So the next visualization is chosen to implement on the Graphene is the power map. Power map is similar to the job viewer, but has the ability to show on the time step rather than the snapshot. The user is listed in the table form. There is two icons of the user, the collapsed user and the normal user. The collapsed user is mean on the job will be displayed at the one summary job, and the normal user will be on the job will be displayed. And for the job component, the job is displayed at the average radar chalk, and the color of the radar chalk indicate for the multi-job or the single job. Like mentioned above, in this visualization, the compute metric will show for the on-time step, and it's showing as the stream. The stream has illustrate the selected metric. The upper stream or downstream is separated by the threshold. The orange will be marked for the upper stream, and the blue will be marked for the downstream. And also another color is red or black will be indicate for no job running on that node. For this visualization, when choosing a particular metric, it's easy to detect the upper threshold. For example, right here, its interesting point is those compute running by a single job and have a different memory power value over time.
Thank you, Nanan Jay. In this presentation, we've given you insight into cutting-edge visualization, monitoring, and management solutions for HPC systems. Along the way, you saw examples of CPU 1 temperatures being higher on average than CPU 2, for example, in air-cooled nodes, which is due to the physical design, and the reverse in water-cooled nodes for the cooling flow is different. We are able to use these tools to understand general characteristics of high-performance computing platforms, as well as detailed application behavior. We collected the telemetry metrics from the baseboard management controllers through newer, more powerful telemetry-enabled iDRAC9, and compared them to older non-telemetry-enabled iDRAC8, using the Redfish API, and correlated these metrics with data from jobs collected from the resource manager. In the future, we expect to extend these methods to other application behavior on jobs. We used these visualization tools that Anand has described: parallel coordinates, job viewers, radar charts, power maps, for mining HPC system and user behavior in an interactive way. When you're able to actually get your hands on these tools, you can actually interact with them much more readily than is easy to show in slides. To make it even easier, we've just exported the visualization tools to open source Graphene plugins that will be made available to allow people to adopt these methods on their own using the Redfish enabled capabilities of their own nodes. So in all of this work, we want to thank Dell Technologies, and if we go to the last slide, also thank their funding partner in this work, Intel. And thank you for viewing this. If you have questions, please contact us. And the easiest way to reach us is through our website, nsfcac.org.